Okay, I have a question for everyone. Hey, I've got a question for everyone. How many have heard of transformer neutral blocking? Pretty good. How many have not? One, two, okay, I got a few. I've got a lot of slides. I'm going to try to roll through this quickly. I need the slides. There we go. Very good. Okay, we've talked about low frequency, high impact events. I don't call this low frequency anymore. It's at least moderate frequency, and it's extremely high consequence. So this is really important. What I'm going to talk about is the vulnerability of the grid and mitigation solution. So we're going to get to the solutions and real data. Well, that didn't work. Here we go. Yeah, there we go. Okay, there's a long history here of both solar weather studies and EMP related to the electric grid. The solar weather papers, we can find them dated back to 1930. There's probably people here that probably have gone back further than that and have seen papers further than that back. The EMP experiments in the Pacific were done in the late 50s, early 60s. There were two EMP commission reports, 2004, 2008. There was the GRID Act, the SHIELD Act. They both died in Congress several years ago. Now we heard yesterday that the SHIELD Act is going to be part of the energy bill. Great news, absolutely great news. There's IEEE power grid papers related to solar storms that date back to 1972. Our work started in about 2009 on this subject, and the Idaho National Labs started maybe a year before us, really getting into this. And I just confirmed that with Professor Baker this morning. Here's the images from the high altitude nuclear tests in the late 50s and the early 60s over the Pacific. This is when they first realized the EMP problem, the EMP threat. They actually disabled some electronics in Hawaii, which was many, many hundreds of miles away, and it was all of a sudden there was a realization that a nuclear bomb above the atmosphere propagates this electromagnetic wave down upon us. That's when it was discovered, a long time ago. And then the solar understanding came in the early 70s, started to be put together in the 70s, where you get coronal mass ejections, solar flares coming off the sun. And they go off in all directions, but when they come our way, we know about it. And they interact with our magnetic field of our Earth, and they jiggle it, and they cause this so-called E3 wave that impacts our power grid. And we see them. If you live in the northern states, or Canada, or Scandinavian countries, or South Africa, you see the effects of solar flares hitting the Earth. Now, just a little perspective here. Here's an image. Boy, it's just barely over the top of the table here. Here we superimposed Jupiter next to the sun. Sun is a big, big ball of fusion going on up there. And you can see a solar flare coming off the sun there. Well, below Jupiter is the Earth. Look at the size of the Earth compared to a solar flare, even when it's superimposed right next to the sun. When it gets to us, it's much bigger. And after it's traveled the 93 million miles. Now, there have been two solar superstorms in our history that we know of. Carrington event, which has been mentioned several times, the New York Railroad storm in 1921. Both of these occurred before we built our power grid. If you look at the evidence of electrical power in our country, we built the grid after World War II. And the power went up during the years of late 40s, 50s, 60s, 70s is when we built the grid. We have not witnessed a solar superstorm since we've had the grid. Do we know what it'll do? We sure do. It's easy, very easy to model and calculate. And it's been done by several companies now in their software, their power flow software. So we have not witnessed a big superstorm while we've had the grid. Now the probability of a big storm hitting, a superstorm, is 12% within the next decade, or 25% within the next 20 years, 2 decades. That's a big number. That's a big number when you consider the consequences of the power grid going down and you can't get it up for months, if not years. So this is a big number. Now this probability was calculated by 3 independent scientists, all totally independent, 3 independent papers, and the number comes out just the same. It's right on, but all 3 of them agree perfectly. Now, one of the consequences of these storms is you saturate the big transformers. You have what they call half-cycle saturation when the DC current or quasi-DC current is in the transmission lines and in the transformers. So when you saturate them, you generate all these harmonics. And harmonics is bad quality power. And the standard, the IEEE standard, is 1.5% for total harmonic distortion. And we exceed this all the time whenever the solar storms are hitting us, even for the small storms. It only takes a small amount of current, and that's been shown in both calculations by Ray Walling on the left there, and in tests that we did out at Idaho National Labs. And just a small amount of current, anywhere from 4 to 32 amps of DC in these transformers, get you well above the IEEE standard for harmonic. And in addition to that, there's been a study done. It's a statistical study by 4 very, very well-known scientists, one of which spoke here yesterday and will be speaking this afternoon, Bill Murtaugh. And what this statistical study showed is they took all the insurance claims and they threw out the ones where there was a known cause of what caused the damage that was being reported to the insurance companies. He threw those out, and then they looked and they found these insurance claims would peak like a month after we had a solar storm. So they attributed those to the solar storms. So the correlation is very high, and it looks like ordinary storms each and every year results in $2 billion plus annually. And this was done data was looked at over 10 years, 2000 to 2010. So everyday storms are causing a lot of damage, and nobody knows what it is. This was a statistical correlation that they found and published. And actually, there's 3 papers on it now. Now, somebody mentioned that we had a big coronal mass ejection from the sun in 2012 that missed us. Here it is. We happen to have a little video that NOAA put together on this. The data from satellites shows the solar flare going out the backside of the sun. Did not come our direction. This is, when they looked at this one, they said this was the big one. This was one of the big ones. And you can see the Earth is over to the right side there. The arrow points to the little yellow dot. That's supposed to be the Earth. And the CME, the coronal mass ejection, comes out pretty much the backside. You can see how large it is by the time it gets out 93 million miles. Now, if you look at the data for these very, very large ejections, on average, they come off about every 7 years. This isn't a 1 in 100-year deal. It's a 1 every 7 years, statistically. But they go different directions. And when I look at this, I say, wow, have we been lucky, or what? If the last one was 1921, the one before that was 1859, now, you can't say that it's due or anything like that. You know, the time clock starts now. The probability is 12% within the next decade, or 25% within the next 20 years. To me, that's a big number. Now, we looked at some data that was submitted by EIS to Maine, to the Maine Public Utility Commission, and what they found was data collected up at Chester, Maine, at a transformer up there, and they found, in one case here, 100 amps of current, and they correlated it to the magnetic field, the rate of change of magnetic field, of 250 nanotesla per minute. 100 amps. We know the big solar superstorm is 5,000 nanotesla. It's 20 times larger. Multiply 100 amps by 20, you're looking at 2,000 amps as possible at a substation up in Maine. There's a scatter in the data here because they didn't have the data that told you what the electric field direction was. It doesn't always line up with the power line. But when it does, you get the higher currents. So that's why there's a max on this, and a min, and a median. But the possibility is 1,500 to 1,000 to 2,000 amps. And that will fry a transformer. There is no doubt. You can talk to the manufacturers and they will verify that. So our unit is a neutral blocking device that we put in the neutral connection, not on the high voltage side, we're on the neutral side of the transformer. And when we detect the current, we put in a blocking element. It's a capacitor bank. That still effectively grounds the transformer. The power stays on, everything operates like normal. We're just grounding the transformer differently. We're grounding it AC-wise, not DC. And it blocks the DC. So you've mitigated the problem. And here what we find in our modeling that we do with Power World is as we add transformer neutral blockers, the collapse of the voltage moves to the right. So we can go to much higher geoelectric fields, much higher EMP E3 fields. E3 and GMD is essentially the same, both the quasi-DC phenomena. So here we raise the collapse point out considerably with putting 25 neutral blockers in the system. And this was done for Wisconsin. This is a Wisconsin run. We do have one unit up and running. It is in Wisconsin. It's at Morgan. When you put one in, it doesn't change the collapse. The collapse. Two more? 2 minutes. Okay, let's go. Also, another benefit is we reduce the reactive power, what they call the VARs. And when you put in 20% blockers in the system, you drop the reactive power demand by over 40%. So there's multiple benefits. Now people talk about procedures, that they can take care of this or mitigate with procedures. We found in our modeling and this was done for Maine, that if you follow the ISO formula of reducing power transmission by 10% under a storm condition, we found no change in the voltage, the collapse voltage, essentially none. So procedures, moving power around, unless you move a lot, if you move it 90% down, but up in Maine in the high demand times, you're moving 1,000 megawatts in the summer or in the winter. The transformers at risk are essentially 5,000 of the big ones across the country. And in our modeling, we find that we can do a very effective job by putting neutral blocking on 1,000 of the 5,000, or 20%. And that could go for a state, could go for the whole country. It's a pretty good number, 20%. And what does that relate to? Our unit is $400,000 per copy. I had a president of a utility up in Canada come up to me and says, how much does that run? I says, 400,000 installed. He said, in our industry, that's peanuts. Peanuts. He said it 3 times. That's peanuts. Well, if you do all 1,000 in the United States, that's 400 million. It's $1.25 per person, amortized over 10 years. It's pennies. It's peanuts. I mean, it really is. And they're a lot less costly than a $10 million series capacitor bank. And we have series capacitor banks in the systems, especially out in western states, the really long lines. Now, the transformers with highest risk are the really big ones, the 345, 765, and if you got ones up toward 1,000,000 volts, yes. That's what we find in our modeling. And Frank Koza told me this morning or yesterday that that's what they're seeing in their modeling as well. It's the big ones, and the modeling shows that the highest currents in these systems that we've studied, the highest geomagnetic currents, induced currents, are at the generation sites. When we start blocking, we find that's where you want to block first. It ends up in the first couple iterations of our blocking modeling. You can also look, and many times these transformers are single phase. Well, single phase transformers have more reactive demand power than other types, 7 times higher than a 3-phase, 3-legged transformer. So it's a single phase, big transformers. And then if you're along a coastline, there's an enhancement factor in generating the geoelectric field. We know it's a factor of 2, it could be as high as 7. Enhancement of the geoelectric field at the boundary, and that goes in about 50 kilometers inland. So where do we have our big cities? They tend to be along a coastline or along the Great Lakes. And earlier, the gentleman from FEMA was saying we lost a transformer in Canada. We lost a couple in Canada. We lost one in New Jersey, Salem, New Jersey, for that same storm. And we've lost several in South Africa for these storms. This is our unit, what it looks like, 8 foot by 8 foot by 12 foot tall. We've tested it. We've modeled it in the University of Manitoba. We've tested it at a lab outside of Philadelphia. We tested it at Idaho National Labs. This is the circuit diagram. It's fail-safe, fail-safe, fail-safe. I can't say it enough because we've got so many safety precautions in here. Somebody asked a question just the other day about what does it do to your neighbors? We modeled here Wisconsin and showed that as you increase neutral blockers along the bottom, you don't really change the amount of current going to your neighbors. It stays the same. And the whack-a-mole effect, if you use 1 or 2, you got to be careful, but you need to put in a sufficient number to really get the advantage. This one's in Wisconsin. Was in Wisconsin for over a year till the engineers got their head around it and got used to it. Now they love it. Engineers say, we need more. It went into operation in March, In June, we had a storm for 2 days, 22nd, 23rd, went into operation 14 times during the 2 days. That's the evidence of it working in a small storm.
And we will have a chance to, on maybe our best practices section, to
We got two.
1 minute, and then
1 minute.
we're going to go
Yeah,
on the
yeah.
best practices section.
Yeah.
But I'll be standing right with you.
Now, on warnings, on St. Patrick's Day, there was a storm. The warning from NOAA came 49 minutes after the storm hit the earth. I don't think procedures are going to work. And then the storm that we were operating under, we got the message 4 minutes before the storm hit. Of course, ours is automatic. We don't need a notice. Here's some things that we've learned. I think I've said most of these. It's a very effective solution, and there we are. Thank you.
Thank you very much. And we will have a chance to hear a little bit more on the best practices panel later this afternoon.